Hello everyone, welcome to another Cube video about internals of Cube library, about details of Cube format, about the data model and everything what goes beyond just usage of our software package. So I proceed explaining the details of Cube format in this case. In previous videos I explained the general format of .cubex file, which is basically tarball, which consists out of the set of specific files. In another video I explained syntax and meaning and usage of the special file anchor.xml. That's basically description of the profile with metrics, with regions and call tree and system tree and so on. And we took a look on some specific details of this format, maybe not all of them, basically basics, but I pointed out where one can find the definition of syntax inside of the source code of Cube library, so that one can work it out, because exactly this syntax, this parser, defines the final format. And in this video we go to another part of this .cubex file, to the data containers, to the part of the cubex file where actually data is stored for every metric. And I will explain in details the all layout, so that one can theoretically, hopefully, create own I don't know, reader for this files using some another library if one wants, if one doesn't like cubeglib, for example. Yeah, okay. At this moment I would remind you to subscribe. If you like it already now, press a like. If you have already now questions, you can put it into comments to this video, or maybe later during this video. Okay, let's start. Here, where it is? Okay, here, yes. So we today, we go cube data container. We will take a look how the byte-wise layout of the data container looks like, and how one can find out where is which data is actually located. So general remark, so one of the main requirements for this data container is possibility to have so-called random data access. So it means that we, for selected metric, for selected call path, and for selected location, we would like to directly find out where is the data, where is the value actually, and we would like to read it out. So I will call it random, not memory access, but data access. Data access, which means basically metric, call path, and location. We remember that locations only have coordinate. We need like position aside .cubex. So .cubex. That's basically one of the requirements, and probably the only requirement. As a result of it, and in generally, it leads to the such property fact that we store the data metric wise. So storage is metric wise. Metric wise. So if you remember from another video, the content of .cubex file is basically anchor.xml and series of files. So let's write it down as well. So content of cubex file, anchor XML. That is the file with description of cube. We we worked out this in another video, and then sequence of such file like 0.data, 0.index, 1.data, 1.index, tralala, 100, let's say m.data, m.index. Being container, it actually can contain many other files. It may be remapping specification and like remapping spec and another service files. But so today we are looking at these files. Exactly, this data and index files, and this number 0, 1, 2, 3 up to the m, that is nothing else than metric ID. And for every metric which has some data, every metric has ID. That's also one of the coordinates. And for this metric we have own set of these files, data and index, and that's what I mean with metric wise. So data is stored separate. Okay. Another point what one has to mention is that we do support zlib compression. So zlib compression, well, zip compression, but we use zlib for that. That's why I call it zlib compression. Supported. Read default. Write. On by configure, basically. So what does it mean? The cube library, CubeW library, by default has disabled zlib compression. So if one would like to produce a cube file, cubex file, which has data compressed using zlib, you have to configure CubeW library with option zlib compression full. Then it will compress the data while writing. So CubeW library only creates cubes, it doesn't read, so it will just create a compressed cube file. CubeLib library can read and write cube files. There is default zlib compression is supported if zlib is found on a system. It means the library will be able to read compressed cube files, but if it creates new cube file in some tool or something, then it creates non-compressed cube file. So that's basically default option is with zlib compression equal read or read only or something. You have to take a look in the help of configure script. If one enables it during configure step with zlib compression equal full, then it will not only be able to read compressed files, but also will create compressed files. We do not put it as default completely on, because our measurements show that from one side you get, of course, compression, but from another side, time to decompress it compensate actually this win of I/O that you have to read less data, and therefore it's it doesn't bring much from our point of view whether to have it always on. Sometimes one really would like to have completely compressed data, so where the data storage size is important, but then the user has to enable it manually. Okay, so in this video I explain layout of non-compressed data. So here no compression, basically, no. Here layout, no compression. In probably next video I will explain how the data layout looks like in the case we switch on the zlib compression, how does it change, and where is actually difference, and so on. So these are important points which I wanted to point out before we actually start to talk about details and specifics. Okay, so let's go to the first. I would like to explain you how the data file is constructed, what is the layout of data file, and then I will explain what is about this index file. Okay, yeah, maybe before going into the actual individual detail, maybe it's worth to point it out that, for example, m data, that is the file which stores actually the data of metric with ID m. So like for example, we measured the runtime of I don't know, foo, then and that is like 1.5 seconds. Then the actual value 1.5 in double representation gets stored, and this number one finds in data file, not in index, not in somewhere via mapping, blah blah blah, exactly there. So if one takes a byte view of this file and seeks to the proper position, one will find out 1.2 as a double value, for example. If that's another integer or some another data, then there will be exactly this byte representation of this data. And in m index, one stores actual mapping, so it stores the mapping, and here is which like for m is already fixed, therefore it's out of the consideration of the pair C node ID, location ID. These are to another coordinate. We call it C node because it's a call path, but we internally use the name, the term C node, therefore C node. It's call path ID actually. ID and location ID. As you remember, in our data model, metric C node, call path ID are coordinates, and in the system tree, only locations have are coordinates. The location groups and system tree nodes, they are basically organizer of the system description. They show which locations belong to the same group, to the same node, and so on. They by themselves, they don't have any coordinates because you cannot assign any value only to them, to like location group or to system tree node. Therefore, only location ID. So basically, index maps exactly this pair through one or another procedure to so-called position. This position is exact position inside in m.data. So it's basically having C node ID, let's say it's 10, and location ID, let's say it's 100. The index file tells me how can I calculate this value position, and then I go on inside of m data file and can using this data find exactly position of this value of its byte representation, and if I know that, for example, these are doubles, then I can read 8 bytes, and then I get a double value for exactly this combination. So that is to this pair. Okay, let's go direct to the actual layout of M data. So layout of M data. Okay, so the layout is actually pretty simple. It's a row-wise storage of data, where is a row that is the sequence of every value for every location, and one row corresponds to some C node. Like C node 0 would have one row, C node 1 have another row, C node 100 or call path 100 has own row of data, row data. So row-wise storage. Every row has the same size, and this size is exactly number of locations times size of the data type. Has the same. Okay, this we can same size. Which is number of locations times size of data type. Like this. So we have inside in representation of one row no gaps. So every location, whatever we have in our system tree, is coordinate, and it has ID, and exactly it has one value, one position inside of the row. Whether this value is 0, 5, 25, or I don't know what, it has it. So even if we didn't measure maybe some value, like for example, we have location which corresponds to GPU, but we are measuring metric which has meaning only on CPU. We still will have a place for the locations corresponding to GPU, at least in our current representation, in our current format. It is made exactly for this requirement, random access. If we know the size of every row, we can jump directly to the position. If we would have the separate row, we would have to either go through the list or something else. So that is important. And data type, that's data type of this metric. So some metric is double, some metric is integer, some metric is complex or whatsoever. So this data type might have 8, 4, 20, 16 bytes. Therefore, the size of the row is the same. And every row corresponds to some C node. So C node 0 will have maybe one row, C node 2, C node 50, and so on. And they are stored one after another. So therefore, layout basically, let me take a look how it looks like here. Another thing is same size and no gaps. Do I call it no gaps? Yeah, how to call it? Yeah, that's basically what I already said. So the neighborhood relationship between the data is like within a row. So that if we have NC and then NL some value, and we have NC and NL plus 1, basically one more, the value. So distance between them will be one in star, one data type, because they are neighbors. Yeah. But however, distance between NC and L and NC plus 1 and L will be number of locations in bytes. So it will be the whole row. That's basically another explanation that we are storing the data row-wise, right? And no gaps. No gaps means every location has position in a row, let's say. Yes, no gaps. Okay, let's mark it like as important. No gaps. Okay, so that's row-wise. So that's basically the important properties. How does it look like to visualize? So as very first in bitwise, so let's do byte-wise representation layout. Okay, so very first thing, if one opens data file, one gets so-called magic string. Magic string. This is depending on whether it is compressed data or not. It might be either so-called cubex dot data or zx dot data, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes or 11 bytes. And this magic string shows us that the data which we are going to read belongs A to cubex, B it might be compressed or not compressed. Therefore we have this magic string. We read always like 11 bytes and see if it is starting with zcubex or with cubex, and then one can conclude. So and then we actually have, like starting from this position, that's probably, let's do like this. Where is this? Here? No. This. Like this. Okay. Okay. And this we have starting directly from this byte. We have beginning of our first row. That is the row with a C node ID star. I will explain why star 0. And for example, it goes here and there it ends. And then we have another row starts, and here is C node ID star equal 1. And here, and so on and so on, we have till we get C node ID star equal M or N, and that's all. That's basically all what we have. We have 11 bytes or 10 to 11 bytes of magic string. And then such row-wise data for C node star equal 0, C node star equal 1, C node star equal 2, or n, and so on, till we have. So in total, every of this C node, in every of this row, if we will do it like this, it's basically sequence of data. So data type for location There is location ID, like from 0, 1, 2, blah 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 blah, number of locations minus 1. Yeah, so the first n bytes are belonging, or that corresponds to the value for location with ID 0, the another one with location 1, 2, and so on. And this is the value. That is actually a byte representation for metric data type value, which is might be double, integer, or anything. So, and therefore we can actually write down the formula. Let's try out to write it down. Formula to calculate position for, let's say, x call path, x location, some combination of IDs, x for call path and xl for location. Okay, and that would be, so position of xc xl is equal. So first, size of magic, right? Plus, that is our first shift basically. Plus, we have to find out which row we have, and then shift within a row. So that's basically we like 0 on the first C node we have a zeros of row, so we do not shift, but otherwise we'll have to jump. Oop. So that's basically a typical standard procedure is number of locations, because every row has data for number of locations values, and then we write here such special thing, I call it cube mapping for xc. I will explain what is that in a minute. And then we jump within actually a row to the ID of this wanted location, which is xl. So, and that is our position in terms of data types. So if it would be double, it is number of doubles. If it is some 32 bits integer, it would be then this short int. Therefore, we have to multiply it with the actually size of data type. And that is basically our formula, which describes where is our data located inside of the m.data. So size of magic is either 11 or 10, right? So let's get another page here. Size of magic is either size of cubex.data, blah, data, which is 10, or set x data, which is 11, right? Size of data types that might be different things depending on what kind of data of the metric it is. If this metric like time, it is stored usually using the double values, then it will be a size of the doubles. which is 8 bytes. It might be also a metric like the number of sent bytes. It would be then integer 64 bits, also 8 bytes. One can define metric which has only integer 16, then it would be 2 bytes. Or one can work with a metric which carries complex values. And complex value is defined as in mathematics real value plus I imaginary value, both are doubles, and it means 2 times 8 values. Or we can also define such metric which is carrying a bunch of data, statistical data or some another data like n doubles. We specify this n in the definition of metric, maybe 10, 20, 155, but they doubles. There is algebra for this data type, but and in this case, this n would be n times 8, and so on. We in a video about data model, I listed actually all supported data types, at least at now. So, and what about this cube mapping? Okay, cube mapping. What does it? What is this? Cube mapping. XC. What is that? Okay, to explain it, let's get another page here. Cube mapping. Cube mapping. X. So to explain it, I have to get a little bit in details. So if you remember, cube has 2 kinds of metrics. Cube has 2 kinds of metrics. Inclusive metric and exclusive. Inclusive and exclusive. This is related to the data which is stored inside of cube file and how it, let's say, behaves or related to their children. Just example, recall for you. Let's observe such situation. Let's do here main, and main calls foo and also bar. Yeah? And let's take a look at metric. Here is, for example, exclusive, and here is inclusive. So, and let's say that would be kind of time metric, runtime metric. Then main was running 6 seconds, and out of this whole total run, foo, when it get called, it was running 2 seconds, for example, and bar was running 3. Oops, that is wrong. Where it is positioned? Here I wanted 6 seconds. It's 2 seconds, and bar was running 3 seconds. So this would be inclusive values because we measure them in total. Like total run of main includes foo and bar. How it looks like if we would like to calculate exclusive value. Like, of course, foo and bar would be the same because there is nothing to exclude. But what's about main? So you have to exclude basically out of total run of main all the runs of children, and this case would be 6 minus 2 minus 3, which would be 1. So we have the one exclusive data and we have inclusive data, right? And as you remember, depending which data we store, we have to calculate another representation. So, for example, if we store data in exclusive format, so it means in our data file we have 1, 2, 3 stored, right? let's say we have no locations, only one byte. Then we would like to get some value. Let's say we would like to have value for main and exclusive value. But we have it already because it's already stored. So we just return 1. Nothing has to be done. Data is there. We just deliver it. But if we would like to have inclusive value, we have to calculate it because we have stored only exclusive values. And how do we calculate? We take our own value, 1, and adds to it inclusive value of all children, which would be in this case +2 +3, and then we get 6, and we return 6. And opposite, if we have stored inclusive values, if we would like to have inclusive value, we just deliver the stored value, but if we would like to have exclusive value, we have to actually to calculate. So in this case, we would have to take a 6 and subtract all the contribution of children with -2, -3 would be 1. Okay? So, and as we see from this short example, different metrics perform or require different calculation. So in the case of exclusive value, I have to if I store exclusive and I have to calculate inclusive value, I have kind of sum up the contribution of children, and if I have inclusive, I have to subtract. So plus minus seems to be not much, but that leads to important difference. If we have inclusive value, if we have exclusive value and we would like to calculate inclusive value, so it means contribution of all children, what we do? We take our own value and we want to sum up inclusive values of all children. So we take first child and would like to have its inclusive value of child. But we don't have this inclusive value, so we have to calculate inclusive value of child. For that we have to take its own value and go to its grandchild, so deeper, and calculate inclusive value of this child. For that we have to take its own value and go in deeper and deeper. As a result, you probably already recognize, we have to perform deep first search inside of the subtree of given call path. And this leads to basically to natural enumeration of all this call path. It's deep first enumeration. So let's write down the exclusive metrics. So exclusive metrics, they require deep first enumeration. And because we we have to traverse the whole subtree all down to the every child, every leaf, in order to sum up everything and get its inclusive value. And inclusive metric, you might guess what we do if we have data stored in inclusive form. Well, if we would like to have inclusive value, we just deliver it. But if we would like to have exclusive value, we actually take own value, which is inclusive, and we have to subtract the sum, so all, of inclusive values of children. So we don't need to go deep. Already on the level of children, we have our data. So it means we go to first child, then we go to second child, we go to third child and fourth child and blah 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 till all the children. We sum them up and then we subtract it from the own value, and as a result we get exclusive value. It's a little bit faster, shorter calculation, but result is that we do not go down deep in a subtree. We actually we stay on the same level, just one level lower, but we stay on the same level. So it's a breadth first enumeration. So that requires, opla, cannot write. Or wide first enumeration. One can find one can find different names for it. So why do we do that? What we want actually to perform this operation fast, we actually would like to have if we would like to make calculate inclusive value out of exclusive data, we actually do the first search. So basically we access first one child, then its grandchild, then its grandchild, and so on. We're going up and down in the subtree and return back. If we would like to have exclusive value out of inclusive value, we actually access data first child, but then second child, third child, fourth child, and so on and so on. In order to profit from so-called speculative reading or caching mechanism of the file system, we actually would like to have data which we require in one operation close to each other, if not in direct neighborhood, but at least very close to each other. So, so that if we go or read from the storage first data for the first child, of course the file system reads more. It thinks that maybe as a next you would access to the very close data, so it provides a whole sector which might be up to 2 megabytes at once. So we actually access to the next and next and next, so we would like to have this data which we require for the calculation very close to each other. And exactly this enumeration provides it. So in the case of deep first, enumeration is going so that all such virtual new IDs basically of the every of every element in subtree is actually continuously enumerated, and therefore we have continuous access to all these elements. In the case of inclusive data, all children are enumerated continuously, and we have them continuous access to their data. So we profit from neighborhood relationship in this case. So, but why we cannot basically use ID of call tree? That's simple. We have only one call tree, but we have two kinds of metrics. Some metrics are inclusive, some metrics are exclusive, and so either if we store from the very beginning all IDs in deep first method, then metrics which will be inclusive, for example, they will they will be then less performant because the data will be spread. Or if we use intrinistic enumeration breadth first, then calculation of inclusive value out of exclusive data will be done not anymore performant. So therefore we actually keep the internal, these IDs which are stored inside of Anchor XML in arbitrary order. We create for every metric own enumeration, and we use this enumeration to locate data in M data, or in the data container. And this enumeration is given by the type of the metric. Another point is the cube file can come out of Scorpy, for example, or Scout, Scalasca. In this case, cube probably will have deep first enumeration of call paths, because Scorpy creates new element in the call tree in a sequence it experiences this call tree during the runtime, and that is usually going up and down in a stack, and it leads to the first enumeration. But it creates also inclusive metrics, and then there is this enumeration not anymore optimal. Another source for cubex files might be some tool which is using kubelib library to create, like it might be remapper, it might be some merging tool, any tool which modifies cubes and so on. And in this, or something very, very custom, in this case there is no requirement or limit how user has to create this call tree. Arbitrary, the order of the creation of every call path is pretty much arbitrary. The only one requirement is if you create a child in a tree, you have to have a parent already existing so that you assign it properly inside of the tree. But it might be first one branch, then another branch, then we get back to first, and it can be wild creation of call tree. As a result, it will lead to absolutely random enumeration of call path IDs inside of call tree, and we cannot use it for performance storage inside of this data set. Therefore, we have to map it, enumerate it additionally, and then use this enumeration for the positioning inside of cube. Data file. Okay. All right. That's basically it about data file. I hope you understand more or less how it is constructed, how the layout looks like. And if you don't understand, put questions in the comments. And at this moment, I will say you press like, subscribe, and yeah, and comment. Okay, let's go to the another part of our data layout or data container, to the index file. So index file. All right. So having this formula which maps actually whole data, all this combination of C-node ID and location ID into some position, one would think that's all what we need. Why do we need more complexity? Why we cannot use this one? Yeah, why? That's exactly the question. Why do we need this index file? So why we cannot use the formula above, but need the m.index. So the formula which I am talking about is actually this one on the bottom. So why? Let's take a look at another example. So let's draw here a little bit some table. Let's imagine we have main calls foo calls bar, as usual, bar calls foo1, and foo1 calls MPI send, for example. And we would like to store two metrics. One metric is, for example, runtime, time, and another metric, number of sent data, for example, data sent, or data, simply byte sent, right? And we take a look at inclusive exclusive variant. So let's see, here is exclusive, and here let's make inclusive. So the time metric, runtime, we usually store it in very inclusive format by definition. So let's say the main was running 5 seconds. So we write it 5 seconds. Out of this 5 seconds, foo was actually running 4 seconds. So let's see, 4. Out of this 4 seconds, the bar was running 3 seconds. So it is 3. And out of this 3 seconds, foo1 was running actually 2 seconds. So we write here 2. And out of this 2 seconds, 1 second, so like half of time was running this MPI send. So 1 second. That is the inclusive representation. That's exactly how we kind of experience it. We enter the main, then happens something, so all calls are happening, and then at some moment we leave the main. We basically take time by leave time, subtract time by enter, we get the runtime of the main. And that includes all runtime of all subcalls. How do we calculate exclusive values out of it? Simple. We take, of course, inclusive and subtract its inclusive value of children. So 5 minus child 4, it's 1. 4 minus child 3 is 1. 3 minus child 2 is 1. 2 minus 1 is 1 and 1. Yeah, I created specially like that, so we have only ones. What we see here is that first of all, metric time has sense for every of these call paths. Yeah? And we can assign it to every of this call paths, and that might be either all eins or 5, 4, 3, 2 ones or something. So what's about byte sent? So we also take a look at exclusive and inclusive. Here we go for opposite. So we take a look at first at exclusive value. So exclusive value means that value we assign to this call without any subcalls. Yeah. So, and in this case, does main send some data? No, we didn't send any data. No data was any recorded. Nothing. So we assign it first as a absent data, like absent metric. It might be 0, but 0 means the send has been happened, but just nothing has been sent. Absent data means the metric doesn't have kind of value for it. So the same is valid for foo, the same is valid for bar, the same is valid for foo1. And actually by MPI send we send some data only. So we can assign data or value for MPI send. So let's say it's 100 bytes. Okay, how does it look like for inclusive representation? So let's go then from bottom to up. So MPI send inclusive has the same value. Foo1 as inclusive means what's data we sent including all the subchildren and everything. And somewhere down in the subcalls, somebody sent the data. This somebody is MPI sent. So we can assign 100 bytes has been sent. Bar also, from perspective of bar, someone inside of the call has sent data. And that was 100. And here was 100, and here was 100. Okay. So this is basically our two different metrics, and we have different representations here. So what we see here is that in the case of time metric, we have a value for every call path. So it's kind of independent whether we use exclusive or inclusive. It's just by nature of the time. Inclusive seems to be more natural. But in the case of byte sent metric, in the case of exclusive representation, we store data only for one call path. So it's only one row out of 5. And in case of inclusive representation, we actually have to store a value for every this call path. So basically this 100 propagates up to the call tree. And from the point of view of data usage, exclusive representation for byte sent is more preferable than inclusive representation, because by exclusive representation we store data only for those call paths where actually some value is assigned. The other values are 0 by default or not existing, and we don't need to store them simply. So in this case, we would gain, let's say, in our storage efficiency up to the 80%. So we are using only 20% of the theoretically needed file size. So instead of 5 rows, we have to store only 1 row. So, which means some metrics are dense populated. The keyword is dense. Another metric are sparse populated. Keyword is sparse. And what can we say more? What we see is that in the case of inclusive metric, because of this propagation of value up the tree, it's more likely that we will get completely dense population of the call tree. So every call pass will get some value assigned, simply because some deep child got its value, so we have to assign to every parent exactly this value, or maybe they will just aggregate and collide. I don't say that will be 100% density, because the value might be collected not only by leaves, but by some intermediate level, basically like Koshmis. So only half of the tree gets propagation, and as a result gets values. But what we see is that in inclusive case, the values do propagate and populate actually the call tree. In the case of exclusive, it stays assigned to the call path where it has been measured, for example. So it doesn't propagate. So we make here we draw some conclusion. So in case of inclusive metric, we have more likely metric. We have more likely dense. Let's do it another color. Let's see, dense. We have dense population. And in case of exclusive, we have sparse population of data, basically. All right. Okay. So what does it mean? So in another words, in the case of dense population, we have every call pass has a value. So basically we kind of made this rule simply stricter, not anymore more likely. We just say, okay, in the case of dense representation, we expect that every call pass has a value. Whether it is 0 or non-zero, it's relevant, so we expect that it has has a value. And in the case of sparse population, not every. So what does it mean, not every? But not none. So it means only selection of call paths. So basically every listed call path. Every listed call path has a value. And that is exactly what we are into it. So whether here is every or every listed, and depending whether our metric is dense or we expect it to have dense population, we use formula, because we know that every value of C node ID, every ID of and every location ID has a value, it means we can calculate its position into the data file and then find this data, right? So dense leads to dense. We use formula, and in the case of sparse, not every C node is there. We have only list of C nodes. But for those C nodes which are there, we can use the same formula. It's just, let's say, formula star, because we just simply need to know which RC nodes are missing and then skip them. So I will explain it how it works. So formula star, let's say, because we still have, even in a sparse representation, we still have row-wise storage of the data. Simply we don't have first row is not actually 0 and second row first and the third is 2. It might be 0, 15, 25, 100, right? So not every C node is simply represented, but they are still stored row-wise. Okay? Okay, that is the basically, so we have, if the metric is inclusive, it's most likely dense. So for inclusive metric, we use directly formula and we use dense calculation or dense population for the data. It means we expect that every C node, every location ID has its value, and this value is stored in a data file. In the case of exclusive metric, we expect that only these call paths are listed which do carry value. We hope that those number of this call paths is much less than the total number of call paths, like in the case of this MPI send, only 1 out of 5. Then we list only this call path, and then we store only these rows, and index actually provides us the list of these call paths. But the calculation of position is then very same, that's why it is formula star. Okay, so how does it look like in a byte-wise layout? So layout of m.index, right? Okay, so as the very first, as in the same way as in the case of data file, first bytes are magic string. So first goes magic string, and let's say magic string. Let's say it is like that. Magic. And this is, in the case of index, that's only one format. I mean, we do not compress index file, so it is only, and that would be cubex. No, come on. cubex.index. This string is our magic string. It has 11 bytes. Is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bytes. And this sequence of bytes basically signalizes us, okay, that data which we are going to read belongs to our cubex format, to index, and so we are safe. At least we can be sure that that's our format. Then goes so-called header. Header, I will explain it. Explain the header right now, and then goes index. And this index goes a little bit further than header. So how the header is constructed? Header is actually exists out of 3 components. So here is one component, second and small. This one is so-called endianes. We have here 4 bytes, or basically 32 bits integer. It's endianes. We might have situations that we made measurement on a machine which is big Indian, so we stored all the data in binary form, everything is fine, and then we copy this file on our laptop, which is little Indian, and we would like to open it. So the value 1.5 should be 1.5 also on laptop, but on laptop all representations of data is flipped. So therefore we store here the value of 1. And because these are multiple bytes, we would have either 0001, or if it is wrong Indianes, it will be 1 byte and then 000, and which leads to I don't remember what kind of value. It's not one value in another representation, and that is the way how we can recognize that's wrong Indianes. Are we unlucky and we have a cube file with wrong Indianes? Then every binary data which we are reading out of file, before we start to process it, to work it out, whatever it is, we have to flip all bytes. It leads to noticeable performance draw, but that is how it is. The another part of this is 2 bytes. So basically only 16 bits. This is a version of our layout, of our index, of our data layout, of everything. Currently we have only one format, so it is now 0, but later on when we get to 32,000 of version, that would be, of course, very remarkable development of very not stable format. Yeah? And the last element, this 1 byte, that basically shows either 0, dense, or 1 sparse. So we have 1 byte, it may be up to 255 of possible indexes. So we have only now dense or sparse, therefore 0 and 1. If we can come up with some another, then would be 2 and 3 and 4. Alright, so in the case if it is 0, so dense format, actually the second or third part of index is not there, it's not given, because we're already done. Once we have read 0 as a format, so that is format. If it is 0, we already know how to calculate position of our data inside of data file. We don't need anything more. So in the case of 1, we are lacking actually this list of C nodes which do have value, and this is the index. And the index is constructed as simple sequence of files of the 32 bits integer. First 32-bit integer, so 4 bytes, and then, so let's do like that. This is size of the index. So we have selected 32-bit. I think if we will ever run into a situation that we have selected number of call passes which do carry value out of total 2 milliards, 147 millions, blah blah blah, then we have quite a remarkable data set. I don't expect that happened ever in our lifetime. Therefore, we think that it is sufficient. And we have another sequence of basically the values. They all are 32 bits, so 4, 4, 4, 4, and they carry actually C node star ID. So this exactly this result of this enumeration, this deep first, the broad first, leads to some enumeration. This enumeration is exactly what is stored here, and only this value is present which has value. So like it can be here like 0, 5, 20, 43, 45, and so on. And position of this IC node ID inside of index is then gives you position inside of data file. So this file, this C node is on the first position. So this cube mapping in this case will be then 0, and then it will be here this. So let's see, cube mapping here is equal 0, here is equal 1, here is equal 2, here is equal 3, and so on and so on. So we basically, if we would like to know where is our data for C node 25 in actual representation of call tree is located, what do? We take a look at the kind of metric. Is this metric inclusive or exclusive? If it is metric is inclusive, it's dense representation, then we take out of this this call tree, we have the inner enumeration, which is brought first. It will lead to another ID, which is then not 20 but maybe 40, and then 40, that is exactly this cube mapping which goes into formula. Then will be 40 times number of locations plus location ID times byte representation, and that gives us seek. So in the case of metric is sparse, then we know we have to take a look at actual the call paths which actually carry some data. Might be also very dense, but we simply make it a one-to-one matching. So we again enumerate, so we get the number, this 40, and then we have to decide, does this call path carry value? Is it MPI sent and some data has been sent or not? So we basically go into the index and go into this index from 0, I mean like 1, 1, 1, 1, and if we find the 40 in the index is actually continuously sorted basically, then its position is taken to find it in cube data file. If this call path is not present in index, it means this metric does not have value for this C node ID. So we deliver the default value, which is usually 0 in the case of normal integer. Okay, that is basically. I hope you understood. If not, put a question into the comments, and nevertheless, give us a like, subscribe, and see you next time.